Welcome to this video. We are looking at A-Level Year 2 Chapter 1 Algebraic Methods. The first subtopic we are going to cover is proof by contradiction. Very interesting topic. One which people find difficult initially, but not so easy, not so difficult afterwards. So let's have a look what this is about. To understand this topic, we need to have a few concepts in mind. The first one is that a true statement always implies a true statement. A true statement can never imply something false. If I say 2 is an even number, and then I say 2 is odd, those two statements cannot imply each other, right? Like 2 is even cannot imply 2 is odd. A true statement cannot imply a false statement. But if I say 4 is even, and then I say 4 is divisible by 2, then the first statement can imply the second statement. The second statement can imply the first statement. It's possible. I can say that 4 is divisible by 2, so 4 is an even number. 4 is an even number, so 4 is divisible by 2. Yeah. Now the second thing I need to understand, or you guys need to understand, is proving a statement is true is same as proving its negation is false. What do I mean by that? Proving 3 is a prime number is same as disproving 3 is not a prime number. Do you see? Two negatives make a positive, right? So if I say right here, disproving not a prime number is same as prove is a prime number. Hopefully you understand what I mean. Proving A is true is same as proving not A. This is the symbol for not. Not A is false. Not means opposite or negation of A is false. So let's look at some examples now to really understand proof by contradiction. The first example we have is prove there is no greatest odd integer. To prove this statement, what I'm going to do is I'm going to assume not A is true. So I'm going to assume, let me use a different colored pen, maybe green, let's say, assume there is a greatest odd number. There is a greatest odd number. But what have I really assumed here? What have I really assumed? I've assumed not A, right? This is same as not A. And what do we know from above? Proving A is true is same as proving not A is false. So I'm going to assume that this statement is true for now, but I'm going to prove it false. So assume there is a greatest odd number, and now I'm going to try to find something which will disprove this statement. I need to disprove this, or I need to contradict this. Contradict. This is proof by contradiction, right? Contradict. Where did the D go? Yeah, there it is. So what am I going to do? Notice it is sufficient for me. It is sufficient for me to find one number which is bigger than the greatest odd integer. So you'll see what I mean. Let me say, assume there's a greatest odd number. Call this P. Call this P. Okay. And now I'm going to say, consider P plus 2. Consider P plus 2. And I'm going to say this is an integer because we should be precise. Consider P plus 2. Since P is odd, P plus 2 is also odd, isn't it? If I add 2 to an odd number, I still get an odd number. P plus 2 is odd. So since P is odd, P plus 2 is odd. And P plus 2 has to be greater than P, right? Because I added something to it. I added a positive number to it. So P plus 2 is greater than P. And what that means is P plus 2 is odd and P plus 2 is greater than P. This contradicts our assumption. This contradicts our assumption that there was a greatest odd number, because if there was indeed a greatest odd number, P, how did we find a number P plus 2 which is greater than P? That should be impossible, right? So that is only possible if the initial statement, which is this one, was false. But we assumed it to be true. Now we have proved it's false. This contradicts our assumption. So no greatest odd integer. That's it. That's this one done, right? Hopefully you understand this one. We just disproved not A. We called this not A and we just disproved it by finding a contradiction. We found one number which is greater than the greatest odd number. That should not be possible, but we proved that it was possible. So this initial statement must have been false. There should not have been a greatest odd number. Yeah, and we achieved what we wanted. Okay, so now we have the second example. Prove that if n squared is even, then n is necessarily even. All right. But if I'm doing proof by contradiction, I need to prove something is false. What am I going to say is false? I'm going to say assume. Okay, maybe this is a wrong color. Let's say this one. Assume n squared is even, but there is a number where n is odd, where n is odd. So as you can see, what have I done? I've taken this implication that n is necessarily even to be false. So I've taken here that assume n squared is even, but there is a number where n is odd. And we are going to prove this is false. So I'm going to take a different colored pen and I'm going to say we prove that is false. We prove that is false. How will we prove that is false? By maybe getting an absurd statement. By maybe getting an absurd statement. So okay, let's see what we can do from here. Now that we know n is odd, since n is odd, n equals 2k plus 1 for some k, for some integer k, right? Because by definition of an odd number, it should be we can write it in this form. Okay, then n squared equals 2k plus 1 whole squared, right? And if I expand this, I get 4k squared plus 4k plus 1. Aha! Now what do we see? We see this is same as 4 k squared plus k plus 1. And since this is a multiple of 4 and then therefore a multiple of 2, this is even, this is odd. And what is even plus odd? That is, let's say 3 plus 2 is also odd, right? So this is odd, is an odd number, some odd number. But guess what? We assumed n squared is even. So how did we get n squared is odd? How did we get n squared is odd? That is not possible unless this statement that we begin with was indeed false. So since we have now that we have proved that this statement is false, we know the original statement is true. We have proved that this statement is true. So by getting this is a contradiction. This, I just write this is a contradiction to our assumption that n squared was even to n squared is even. So now we have proved the original statement that if n squared is even, n is necessarily even. We have proved that there cannot be a single number where n squared is even but n is odd. Such a number does not exist. That's what we have proved. Okay? Hopefully you now understand proof by contradiction.